We're going to start chemistry today. We're doing chapter 10 in your book, The Building Blocks of the Chemical World. Right, so starting with atoms and elements, I have the learning intentions here, outline how our understanding of matter has evolved over time, explain what an element is, and identify chemical symbols for a number of elements. A lot of this you're going to probably be familiar with already. So just to this idea of how it's evolved, there's been an awful lot of scientists, and even in ancient times, not so much scientists, but initially the concept of atoms or elements, I suppose, would have been the ancient Greeks. And you might have heard of this. They said that everything was made up of four elements. They're here: earth, air, fire, and water. That's what everybody believed at that time. When I say they weren't scientists, academics of their day would have been a bit of everything. So they would have been like philosophers, physicists, chemists, doctors, painters, sculptors. They would have done kind of a little bit of everything. So they wouldn't have been scientific specialists or anything. And this idea of like a scientist now, if you want to put theory forward, so the idea that everything is made up of these four elements, you would have to at least either theoretically or practically provide some kind of proof. And they wouldn't have investigated any of these ideas. So like, look at the difference in time. Like, that was 2,000 years ago, and 200 years ago was when they started to get some kind of an idea of what atoms and elements are as we know it today. So very important name, John Dalton. Okay, so John Dalton developed a theory about atoms. He was a scientist, and he did scientific investigations. So he was the first to suggest that everything was made up of tiny particles called atoms. So that's what atoms are. Atoms are incredibly tiny particles that basically make up absolutely everything in the world around us. They are absolutely tiny. So like I think it's approximately 2 million atoms would fit in a full stop that's printed on the page in your book, just to give you a kind of concept of size. Dalton also suggested that some substances are made up of atoms that are the same as each other, so we'll talk about that. So some substances are kind of what you class as pure, so no matter how many times you break it open, it's only got the same type of atom. So an example would be gold. So if you have a piece of gold, no matter how many times you break it up, you will only find gold in there. Okay, so that's a particular type of substance. And then Dalton kind of expanded his theory a little bit, because obviously okay, sorry about that interruption. Anyway, what I was saying was that we said that Dalton suggested everything was made up of tiny particles. We said that some of these atoms were the same type of particle. And then he expanded the theory to include where you took kind of one of these pure atoms and a different one of these pure atoms, and you combine them together. And that was making new substances. So that's where you were kind of deviating away from these all pure substances. And much of what Dalton discovered 200 years ago is absolutely correct. He didn't go into any great detail as to how these substances combine or anything like that. That took other scientists. But his theories were very valid and still are. And so I suppose the main thing that Dalton gave us was this idea of an element, and he kind of gave us the first idea of elements combining to make compounds and molecules. So what is an element? It is a substance made up of only one type of atom. So as I was saying, an example of an element would be gold. If I have a look, I have it here somewhere. Yeah, here. So here's the periodic table. If I pick any of them, so here's sodium, lithium, beryllium, move over here, nitrogen, oxygen. If you take any of these or find any of these, a lot of these ones over here, these metals are like they would occur in nature. So if you find a piece of sodium and you break it open, no matter how many times you break it, it will only be sodium. Okay, so that's why sodium is an element. It's made up of only one type of atom. No matter how many times you break it, you won't find a different atom in there. And the symbols. So each element has its own name and chemical symbol. Um, they're accepted all over the world so that everybody uses the same symbols. Most of them are English or based on the English name of the element, which is handy for us, obviously, because that's how we know them. You will notice some of them are not. Um, they're Latin names, so I'll show you now. I think I just mentioned sodium there anyway, but they're less obvious, I suppose. And then some of them are named after the scientists who discover them. When you're writing a chemical symbol, it's always a capital letter, and then if there's two letters in the symbol, it's capital and then small. So like if we look, if I go back here again, right, so Li there. Li is lithium. That makes sense. It's English. Be is beryllium. Again, that's based on the English. Mg is magnesium, based on the English. Now look here. Na is sodium. Okay, so that's not based on English. That's Latin. K is potassium. So again, not based on English. So some of them you're just going to have to kind of, I suppose, learn over time. You would want to have kind of a decent working knowledge of these kind of top 4, even top 2 rows over this side. So like there's a few of them that you'll see in questions coming up again and again and again, a few that you'll have heard of. There's a few further down that are quite important. But anyway, you get it on. So that's the idea of how they name them. Always a capital letter, sometimes based on English, sometimes based on Latin, and sometimes named after the person who discovered it. Okay, so this is really what I want to get to, subatomic particles. So calculating the number of protons, neutrons, and electrons in an atom using atomic number and mass number is our first learning intention, and classifying protons, neutrons, and electrons in terms of mass, charge, and location. Okay, so this is incredibly important. All right, so we have an atom. Now, just like I was saying, Dalton didn't kind of do it all. You know, he developed the theory. He started the ball rolling. He wasn't on his own. When they were developing the atom, so when they discovered the atom, they assumed the atom was it. As in, you couldn't break it up. It was a solid piece, and you couldn't break it up. Then I think the earliest version of the atom came from a guy called Thomson. And Thomson developed what was called the plum pudding model. So what he said was that here's the atom, okay, and it's this like solid thing, and then the electrons were like little plums embedded in it, kind of like that. So that was kind of a prevailing theory for a while, and then a guy called Rutherford came along, and he did a very famous experiment called the gold leaf experiment. And basically what he discovered was that with Thomson, he thought this whole thing here was positive, and then these little negative plums, I'm using inverted commas here, negative plums, were kind of stuck into the positive. What Rutherford discovered was that actually the positive charge was kind of centered in one place, like this, and the electrons were all kind of around it. And he discovered that positive charge was not only centered in one spot inside the atom, but it was also really, really small. So like an idea of how small it would be if you took a ping pong ball and put it in the center of Croke Park. The ping pong ball would be your nucleus and Croke Park would be your atom. So tiny, 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 tiny. And then he said that all these electrons, these negative charges, were all kind of floating around. And then it took another scientist called Bohr to tell us about how the electrons were arranged. Okay, and he actually came up with this. It kind of looks a bit like, so the nucleus is here. I'll talk about this in a bit more detail. And he said there was all these like kind of like orbits, you know, kind of like the rings of Saturn or something, and that the electrons actually sat on these like that. So that instead of with Rutherford, they were all just all over the place. There was actually structure to them, and they were sitting in these little rings. Okay, so there was theories after Bohr as well that if you go on and do leaving cert chemistry or chemistry in college, that idea of the rings gets much more complicated. But all of these scientists played a part. So starting with Dalton, following on Thomson, Rutherford, and there were other scientists that helped kind of organize it as well. So they wouldn't have anything to do with the structure of the atom, but they helped to organize one atom with respect to another one. So, you know, why does lithium come in before sodium type of thing in the periodic table? So plenty of scientists fed into what we know today. So essentially what we know is, you can kind of see it here. So in the center, in here, we have the nucleus. Inside the nucleus, there are two what we call subatomic particles. There's the word there, subatomic, okay? And the two things that sit in the nucleus are the protons and the neutrons. The protons are positively charged, and the neutrons, you can get it from the name, are neutral. Okay, so overall, the nucleus is positively charged because it's holding positive charge and neutral charge, which means overall it's positive. Okay, and then out here in the rings, their picture of rings is much nicer than mine, but out here in the rings, these little balls here represent the electrons, and the electrons are negatively charged. Okay, so inside the nucleus, we have our protons and our neutrons. Protons are positive, neutrons are neutral, so overall the nucleus is positive because of what it holds. And then outside of the nucleus, on these shells or rings, we have the electrons, and the electrons are negative. Now overall, an atom has to be neutral. Okay, so what that means is the number of positive charges, your protons, and the number of negative charges, your electrons, have to be the same so they cancel each other out. So if you have an atom with 6 protons, you know that that atom needs to have 6 electrons so that overall the pluses and the minuses cancel each other out and the atom is neutral. Okay, little thing here, I've kind of talked about all this now. So your subatomic particles, your proton, where do you find it? You find it in the nucleus, so that's there. It is a positive charge. Okay, I'll talk about the mass in a second. Your neutron, you also find in the nucleus, and it has a neutral charge or no charge. And then the electron is the last one. You find it orbiting the nucleus in the shells or the rings, and it is negatively charged. Okay, now mass-wise, it kind of talks about it down here. Protons and neutrons have pretty much the exact same mass. It's not identical, but it's very close. So they've pretty much got the exact same mass. The electron then is, you can see it here, almost 2,000 times smaller. Okay, so the electron is really, really small compared to the proton and the neutron. And the protons and neutrons are pretty small themselves. Okay, so all of that is very, very important and you need to know it. Okay, so now, when you look at the periodic table, go back to it here, you can see all the way around it, there's like numbers. See, there's a 5 and a 10.8, a 6 and a 12, a 7 and a 14, and so on, okay? These numbers have significance, okay? The little number, so the smaller number, just change the pen, is the atomic number. So the smaller number is the atomic number, and that tells you the number of protons in this atom. The bigger number then is called the mass number, so that's your bigger number. And that tells you the number of protons plus the number of neutrons. Okay, so if we do this, and they've done it here, but I'll just do it with you. So to break this apart for lithium, the atomic number, or the small number, is 3, which means we know lithium has 3 protons. Yeah? The mass number, the bigger number, is 7. So we have to do the 7 minus the 3 to get 4, and we know that there are 4 neutrons. Okay? So the bigger number is protons and neutrons. If we knew that there was 3 protons, we just subtract the 3 off the 7, and now we know how many neutrons there are. So there are 4 neutrons. So the only other thing then we need to figure out is the amount of electrons. And if you remember, I said that an atom overall has to be neutral. So that means the number of protons and the number of electrons have to be the same in order for the atom overall to be neutral. Okay? So maybe look over that a couple of times to make sure you understand where I'm getting this from. Will we try one more? So if I go in here, I'll take, no, I won't do that one because that one's a bit awkward. Let me see. We'll do beryllium. So beryllium is 4,9. Okay? So if I go in here, I'll just put it at the side. Beryllium 4,9. So the small number, the atomic number, is 4, and we know that there are 4 protons. We get that directly from the small number. To get the number of neutrons, we have to subtract. So we do big number minus small number, which is 5, and that's the number of neutrons. And we get to number of electrons. The number of electrons will have to match the number of protons. So we know if there's 4 protons, then there's 4 electrons. Okay, so hopefully, sorry, invasion number 2. Right, anyway, so that's how you figure that out. Okay, so what I might do is leave it at that for today, and we'll pick up there, what day is today? Thursday, so we pick up there on Tuesday. So what I want you to do is go through this, obviously listen to what I'm saying, and take notes down into your copy as if you're in class. You don't need to write everything down, just the main things I talked about. So up here, the main thing would be Dalton, his contribution. You would need to know the elements, the definition of an element, without a doubt. You wouldn't really need to write anything about the chemical symbol. I suppose it's just that you need to know that there are chemical symbols. This is all so important. Okay, so you need to write down all this stuff I gave you out here at the side. That's just me kind of, filling in blanks for you. You don't need to know that, but you do need to know the way the atom looks now. So you need to know that the protons and the neutrons are inside the nucleus. You need to know what charge they are. You need to know the electrons are on the outside. What charge is that? And this little box here is incredibly important. So the names of them, their masses. So the fact that, so the mass is like, I don't know if we have done this actually, the mass is like what, if you put them on a weighing scales, what they would weigh. Okay, so I'm not actually giving you what they weigh here. I'm just telling you that the proton and the neutron are the same, and the electron is almost 1,000 times smaller. Okay, so you don't need to know their actual weights yet. You do need to know their charge, and you do need to know their location. And then this is incredibly important. So using atomic and mass numbers. So what are atomic and mass numbers first, and then using them to tell somebody how many protons, how many neutrons, and how many electrons there are inside a particular element on the periodic table. All right. So this document that I keep flicking to over here is going to be your homework. Okay. So protons. Yeah. So we won't do 16.10 at the moment, the fully labeled diagram. We'll do the diagrams next week. There's enough content in that for now. So I'll put this up. I've given you the periodic table, so you don't even have to look it up. This is all about protons, neutrons, and electrons. And then this 16.9 is give the number of protons, neutrons, and electrons in these atoms that they've given you here. Okay, so don't do 16.10. I'll include that in next week's homework. I might actually take it out. All right, so I hope you're keeping well. And the due date on this will be start of science class next Tuesday. All right, bye.